Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to the Power Electronics lecture series at ComSets Ahmedabad. In this lecture, we shall discuss the single phase AC voltage regulator with RA load. In the previous lecture, we have discussed the single phase AC phase controller for resistive load. As we know that the AC phase controllers are classified into single phase and three phase AC phase controller. The single phase furtherly classified into bidirectional full wave and a unidirectional half wave AC phase controller. Likewise, the three phase AC phase controller are also classified into unidirectional half wave and bidirectional full wave AC phase controller. In this lecture, our focus will be on the bidirectional full wave AC phase controller with RL load. Figure 3a shows the circuit diagram of single phase bidirectional AC phase controller with RL load. In this figure, Vs is the input. The two thyristors S1 and S2 are used to control both the positive and negative half cycle of the input supply. We have RL load and V0 is the output voltage. For the positive half cycle of the input supply, we have polarity like this. And for this cycle, S1 is in the conduction mode, S2 is in the blocking mode. We need a gate pulse at the gate terminal of the S1 to turn it on. So at omega t equal to alpha, we triggered S1 and current starts flowing through it, and it goes like this and through the load and goes back to the source. And we are getting the output voltage like this, and the current which lags the output current which lags the output voltage, it increases slowly. So for this current path, the circuit looks like half wave controlled rectifier. So by applying Kirchhoff voltage law, we can solve it for the instantaneous value of the output current. So by applying Kirchhoff voltage law, we get this relationship or this equation where Vm sin omega t is actually equal to the Vs of t. R I naught of t is actually the voltage drop across the resistor, and L d I naught of t by dt is actually the drop across the inductor. From this relation, we know that the inductor always opposes the instantaneous change in current flowing through it. If it happens, the infinite amount of voltage is induced across the inductor, which is not possible practically. In other words, if dt intervals approaches to 0, then VL is equal to LdI by dt, then VL approaches to infinity. So inductor always opposes the instantaneous change in current. So that is the reason that current lags the voltage in inductor, and it gradually increases. So this is a first order differential equation, and it has a complete solution which is equal to the transient solution plus steady state solution. So after solving it for I naught of omega t, we get this result. Clear? So comes to the operation of this circuit. At omega t equal to pi, the polarity at the input side reverses itself. So, but at omega t equal to pi, the S1 is still conducting. Why? Because I naught is not equal to 0. So at omega t equal to beta, the I naught becomes 0, and we get the output voltage like this up to omega t equal to beta. So at omega t equal to beta, the I naught becomes 0. The thyristor S1 is now turned off, and from beta to pi plus alpha, both the thyristors are off. We are getting zero output voltage and zero current, and we know that the VSW, which is the voltage across both thyristors, which is equal to this, and now both the thyristors are in blocking mode. So where beta is the extinction angle at which current returns to zero, and we can solve it numerically by using this relationship. We know the value of Vm, the impedance, which is equal to this one, and the theta, which is equal to this one, which is the load angle or the phase difference between the voltage and current waveform. We know the omega, which is equal to 2 pi f, and tau, which is the time constant, which is equal to L by R. So at omega t equal to pi plus alpha, we triggered S2, and we are getting the output voltage like this, and the output current like this, which is increases in the opposite direction now. So the current flows like this through the S2 and goes back to the source. When S2 is in the conduction mode and S1 is in the blocking mode, the red line shows the current path for the S2 when it is in the conduction mode. So at omega t equal to pi, again the polarity at the input side reverses itself, but still S2 is conducting, due to the reason that S1 the current I0 will not is not equal to 0. So current becomes 0 at beta equal to pi, at omega t equal to beta plus pi. So at omega t equal to beta plus pi, the I0 becomes 0, and now the S2 is turned off. So for the interval from beta plus pi to the 2 pi plus alpha, both the ACRs once again in the blocking mode, and we are getting VSW, which is the blocking voltage across both the thyristors. So the output voltage again for this interval is 0, and the output current again is 0 for this interval. So at omega t equal to 2 pi plus alpha, once again we triggered S1, and the same procedure is happened to the rest of the circuit as we discussed earlier for this positive half cycle. So the process repeated itself alternatively for positive and negative half cycle. Clear? So we can summarize the operational modes of the single phase bidirectional AC phase controller with RL load like this. The conduction angle is defined as the gamma is equal to beta minus alpha. So this is the conduction angle for SCR1 for S1, this is the conduction angle for S2, the thyristor 2, and likewise this is the conduction angle for again S1. So this is the point beta plus pi, this is the point 2 pi plus alpha. From these points you can easily compute the conduction angle of any SCR. This is the conduction angle for S1, and this is the for S2, and likewise this is again for S1 and this is again for S2. So you can easily calculate or compute the conduction angle for any SCR. So for the intervals in between pi and beta, at omega t equal to pi, the source reverses its direction, but the thyristor S1 is still conducting, and we are getting this negative spike at the output. Why? Because the load current is not equal to 0, and it becomes 0 at omega t equal to beta. Likewise for the interval 2 pi to for the interval beta plus pi 2 pi to beta plus pi, the at omega t equal to 2 pi, the source reverses its direction and S2 is still conducting, and S1 is not turned on. Why? The load current is still flowing, although it is in the opposite direction, but it is not equal to 0. So at omega t equal to beta plus pi, the output current becomes 0, and after that we can trigger the S1. So we can say that for all these intervals, both the ACRs are in the blocking mode, and we get these voltages across the SCRs. So when the conduction angle equals to pi, one of the SCR is always conducting. One of the SCR is always conducting, and we are getting the same output voltage as of the source. The power delivered to the load is continuously controllable between the two extremes corresponding to the full source voltage and 0. So it is obviously we can control the voltage between the two extremes and 0 is from this point to this point, and also 0. So we can control the full AC source voltage. And also we know that this is a simple RL circuit, and we can analyze it by using a simple phasor analysis techniques. So now we are computing the performance parameters for the single phase bidirectional AC voltage controller using RL load. In figure 5a, the thyristors S1 and S2 are used to connect the load to the source when we apply gate pulses on S1 and S2. If we are not applying any gate pulse on the S1 and S2, we are disconnecting the load from the source. So to achieve variable V0, we always need high frequency gate pulses on the S1 and S2. To compute the RMS value of the load current and load voltage, we always need to apply the RMS value definition on the one complete cycle of the output current and output voltage. So to compute the RMS current, we need to apply the definition of RMS quantity on the one complete cycle of output current. So we can see that this is the complete cycle of output current. We can set the points for the integration for the intervals used in the definition of RMS current calculation. The alpha, pi, beta, alpha plus pi, 2 pi, and this point is beta plus pi, and this is 2 pi plus alpha. So by using these points in the definition of RMS quantity for the current calculation, we achieved this result. And so far, for the calculation of output RMS voltage, we can apply the RMS definition on the one complete cycle of the output voltage. So let take a complete cycle of output voltage, which is this one. I'm taking this one. So now we can set the points for the integration. This is a pi, beta, pi plus alpha, 2 pi. This point is again beta plus pi, and this is 2 pi plus alpha, and this is 3 pi. So we can say that these are the points used in the definition of RMS quantity calculation. You have learned previously in many lectures that how we can apply an RMS definition for any quantity. So power absorbed by the load is determined by using this relationship, which is equal to the power absorbed by the resistor is equal to the RMS value of output current squares times the resistor the resistor value R, The RMS current in each SCR can be computed by using this relationship. The average load current is 0, but each SCR carries 1 off of the current waveform, making the average SCR current this. So average current is 0. Why? Because of the symmetricity of the current waveform at the output, or the symmetricity in the waveform. So average is 0, but each SCR carries for 1 half cycle. So if we are taking the limit for 1 half cycle like alpha to beta, then the SCR current can be computed by this relationship. So let's have an example on the single phase bidirectional AC voltage controller using RL load. In this example, we have a voltage source of 120 RMS at 60 Hz, and the load is RL combination, series RL combination with R equal to 20 ohm and L equal to 50 millihenry. The delay angle alpha is equal to 90. We need to determine an expression for the load current for the first half period, second the RMS load current, the RMS SCR current, the average SCR current, the power delivered to the load, and the power factor. For the first part, we need to compute the load current for the first half period. So we are using this expression, as we know that for the first half the value of the load current is this: Vm by Z sin omega t minus theta minus sin alpha minus theta e raised to power alpha minus omega t over omega tau. So we need to compute the unknown quantities. So by using these formulas, we are computing the unknown, having the value of Z 27.5, by computing the theta, which is equal to 0.756 radians, by computing computing the omega tau, which is equal to 0.943 radians, and the quantity, which is again unknown, Vm by Z, which is the current 6.18 ampere, and the alpha, which is given in degree, is also converted into radians, 1.57 radians. So the current expression for the first half period is this one. So putting all the unknown quantities and their computed values in this expression, we get this expression of the current for the first half period. We can also compute the extinction angle beta by setting the omega t equal to beta in the above equation, and we are getting beta, which is equal to 220 degree. And we can also compute the conduction angle gamma, which is equal to beta minus alpha. So here we can clearly see that the conduction angle gamma is less than the pi, which means if conduction angle equal to pi means 180 degree, then the output voltage waveform is similar to the input waveform. The RMS load current can be determined by this expression, and we have a value of 2.71 ampere. The RMS current in each SCR can be computed by this expression. So we are getting 1.92 ampere of RMS SCR RMS current value. Average SCR current can be computed by this expression, and we get this value 1.04 ampere. Power absorbed by the resistor is computed by using this expression, and we are getting 147 watt. Power factor is determined by this expression, where P is the real power, S is the apparent power, which is the product of the RMS quantities of voltage and current, and can be computed, and we need to put all these values. We have a real power 147 watt, and the RMS value of values of the voltage and current 120, and it is a series circuit. The RMS value of the output current and the input current is same, so 120 times 2.71 gives us the apparent power, and by this expression we get 0.45 or 45% of power factor. Thank you very much for your patience.